Randy, start recording. Great, I'm recording here too, thank you. So after that, we'll have Robert Moore with his redundancy, autopilot redundancy system. Then I'll be talking about ship landing, and finally David Buzz talking about cloud configuration. We'll also have a little bit from Nick Kay talking about the ESP32. He had issues yesterday with Zoom, and he'll be using some of David's slot for Buzz's slot for that. All right, so over to you, Paul, for your GNC update.
Well, good morning, everyone. The GNC update, it's a mixed bag. I wanted to cover some of the changes that have been made to the EKF since the last conference. Just a very quick rundown through looking at the pull requests that have gone in and some of the new features that have been added. There's not too much in that area. And then there's been a bunch of, bugs and things that have been fixed up. Then the major topic, and what I wanted to spend the most time on, was to talk about some improvements to plane height control. I've got some ideas there, and I've been, coding and testing a work in progress branch with some new concepts. I'm going to run you through those, the underlying theory, why I think these changes could be of benefit, and also go through some of the flight test results. And then lastly, a log which a former colleague of mine shared with me and said it's okay to share it with the wider RG-Pilot group, because there's some learnings out of it. It was a twin-engined UAV that lost roll control during its initial flight test due to an issue with loop tuning and Sideslip, which is interesting. And I thought I'd highlight some of the things that came out of that log analysis. And if my voice fades, I might have to go and grab another water or a lemsip. We'll see how it goes. Okay, so in the last 12 months, we've moved across. We're now using EKF3 as the default estimator for our stable releases. I don't know if Antenna Tracker is using it now. Maybe somebody can chime in on that. But my understanding is that EKF2 is still being kept as a selectable option if the board's got more than 1024 kilobytes of flash. So our high feature boards have got the ability to also run EKF2 if users want to do that. It's been fairly, the code base has been relatively stable over the past 12 months. We've had eight features. Some performance and stability improvements. Bug fixes have been the largest number of contributions, and what's encouraging is non-contributors and people like Randy and Tridge doing a lot of contributions to EKF and others, which has been really encouraging to see, because I don't want to be the only person that can maintain that library. Okay, so let's have a look at the some of the new functionality. Probably the one to note for which was of interest, and that is we've implemented what we call a moving origin for the EKF. So in other words, as the EKF, as the vehicle flies or drives or sails, we move the origin of the EKF with the vehicle. And the reason we do that is because what we were running into was that for vehicles that were doing very long distance navigation, for example, sailboats doing, oceanic type of survey work, if they got too far away from the initial starting point, the flat Earth and the way that the UK and the way the libraries would project the northeast delta onto the original origin was causing some stability problems. Once you got out past 250 kilometers, it started to get a little bit, the errors would start to build up. So now we move the origin, move the origin along with the vehicle. It's transparent to the users because all the data is sort of in terms of the output from the EKF, that's a transparent process. It just means we don't suffer from the limitation for long distance navigation. Having said that, we don't do round Earth navigation. It's still a local northeast down navigation frame for our for our EKF. And I don't think any of our libraries for our vehicle types are currently doing round Earth navigation. So if you want to do round Earth navigation, you still have to effectively put in a series of intermediate waypoints to achieve that. Okay, we had another change, which was we've now got the ability for to externally select the non-magnetometer yaw source. If you remember from previous year's presentation, we'd implemented this method of aligning the yaw angle of the vehicle just using IMU and GPS. You know, we have this emergency, it's called a Gaussian sum filter that runs a bank of EKFs, and effectively it means that with enough vehicle motion, we can detect the yaw, and it's been very handy for preventing flyaway. So if the vehicle does get a bad compass yaw and starts to fly away, the acceleration makes the yaw observable, we do the reset and it recovers. The number of resets was limited previously. Now what we've done, if we actually enable an external entity, for example, like a Lewis script, to reset to the Gaussian sum filter yaw as many times as they like. And thank you to Randy for putting that in. We've also got improved support for being able to switch in scripting between GPS and optical flow, which is this pull request. And the reason that's important is because it's very hard to come up with a set of internal heuristics within the EKF that will know when you can stop using your GPS or when you can stop using your optical flow, because it was very much depending on hardware, the sort of mode of operation of the vehicle. In other words, to make the correct decision as to when to fall back to optical flow or start using GPS, it was contextual. And to do that properly required information that the EKF did not have access to. So Randy's put in some good support there so that we can switch between GPS and optical flow, and we can control that via Lewis scripting, enable you know, users to customize that fallback behavior. Okay. Okay, we've got some improved support for visual odometry to be able to align the yaw to the GPS, to using the movement of the vehicle and the GPS. One of the reasons is, I don't remember the background behind this pull request. So maybe Randy can tell us what it was that had prompted this change.
Yeah, before it was, you could realign to, I think, the visual odometry, you could realign it, you know, like a 3D camera, you know, using for SLAM or something like the Intel, you could realign it to the compass, but you couldn't, we couldn't realign it in case the GPS was being used for yaw for some, you know.
Okay, so this is when you got the two antennas.
Yeah. And so I think my main sponsor wanted to fly indoors and outdoors. You know, from inside of a warehouse to outside of a warehouse, and they wanted to use the GPS for yaw when they were outside and the 3D camera when they're inside, so they needed that transition.
Well, that makes sense, because I mean the magnetometer is going to be pretty inaccurate as you come out of a warehouse, so it makes sense that they would want that. We've got another pull request, which this is important for fixed wing pilots that are running multiple airspeed sensors, so that we're able to use the airspeed sensor that the EKF is for the active lane, because we have something called affinity with the EKF, which has been in for over 12 months now. And the affinity feature means that you can assign, you know, airspeed sensor 1 to EKF, to the first EKF, and a second airspeed sensor to the second. That's got the benefit that if one of your pitot probes becomes blocked, you get large innovations, that can cause a lane switch. And then you've got the active lane, and then this enables the control loops. So Now, Tridge, if I remember this PR correctly, that selection of the EKF and its corresponding airspeed sensor, that will also affect the airspeed sensor that's used by the plane control loops.
Yes, that's right. So the plane control loops go and ask, which airspeed sensor to use. So the primary, when it switches, it will switch the primary inside the airspeed library.
Yeah. Okay. So we know that's a good feature to have if people are running multiple airspeed sensors. We've got some support added, an odometry Madlink message. And this was providing support for a specific visual inertial odometry system.
That's the one that
So
Modal AI uses. So Modal AI have a very nice visual odometry system, particularly targeting copters, and it's that message incorporates, it sort of combines the position, velocity, and into one, and attitude into one message.
Yeah. Okay, so that's pretty much it in terms of features. It's really been, these are really been about integration of some new sensors, improving sensor fallback, probably been able to fix up the limitation on long distance navigation was probably a big one to have. There's some other changes which I've bunched into what I call accuracy improvements or performance improvements. And that's really related to the ability to be able to run the EKF as a double precision, using double precision processing. Because if you've got a high spec processor like an 8.7, we can take advantage of the additional accuracy in terms of double precision floating types. And we also have the ability during replay, and when you replay a log, to decide whether you're going to replay it with single or double precision and evaluate the effect of that on the performance of the filter. And what went along with that was some improvements to the mathematics or the derivation for the covariance prediction, which has really, and this change, it was a subtle change, and not to go into the details here, but there are two different ways that or industry, if you like, accepted methods. So how you go from a set of quaternions, which describe the orientation, because we use quaternions in the EKF to describe the rotation of the vehicle. And you can then define the rotational direction cosine matrix, which rotates, a vector from body frame to earth frame. And there are ways to express that as a function of the quaternions. And there's one method, the one I'd use, which is pretty much the default you'll find it in aircraft dynamics textbooks. Flight dynamic simulations. And there was an alternative method which is used by the computer graphics industry. And a colleague on another project had found, when we were trying to improve, debug, some stability issues with when you start to tune the filter, found that for a reason which we still don't fully understand, we think we generally understand why it's working, but if you go to the version of that, transformation from quaternions to rotation matrix using the equations that are generally used by the computer graphics industry, it actually results in equations for the covariance prediction which improve the numerical stability. And we now have a bigger range of tuning parameters that we can use. So what this effectively means is that if you have a good quality IMU, we can now afford to turn down the process, or if you like, the IMU noise parameters or the bias error parameters to reflect a high quality IMU without having to be concerned about the filter running into stability issues. So that's really made tuning of the filter a less hazardous task. Not that very few users ever touch the tuning parameters, but there have been some companies, with high quality sensors that have gone down the path of tuning the EKF. Okay, that's the accuracy improvements. And then we get I'm not going to go through all these bug fixes. There were numerous, these are some of them were observable behaviours. These are just in response to reported issues, corner cases. Some of them were things like the missing covariance row reset, pull request. That wasn't affecting the results, but had the potential to. It's in there as a bug because you don't want to be failing to reset one row on the covariance matrix when you do a reset for one of your sensors. So I won't go through those, but you can see that the emphasis is now moving more towards bug fixing and maintaining features. We're fairly feature complete with the EKF at the moment, and the longer we keep using it as a stable code base and just keep responding to the reports, and we just keep improving it, pulling defects out one pull request at a time, and it's all about improving the reliability or improving the trustworthiness of the code. And so it's been encouraging to see the amount of feedback that we've had. In fact, we've had users that have gone in, have decided to do a review on the code, and they've found things which have escaped us. They've gone through the code and just picked up an indexing issue just with a code review and have reported that. So we greatly appreciate users or developers that spend the time to do that. So thank you to everyone that contributed. And we've got others which are more along the lines of code improvements. So these are cleanups, make the code a little bit more efficient and really affect functional behaviors or performance. Pardon me while I clear my throat. So that's it with that's a very top level, 50,000 foot view of the EKF and what's happened to it in the past 12 months. Now, what I wanted to talk about was the height controller for plane. Now before I go on to that, were there any questions about the EKF?
Sorry, Randy here. I guess looking forward, I really haven't thought about this very much, but I just quickly chatted with you on Skype about it a week ago or so. But there's definitely, of course, always interest in, well, dead reckoning. Actually, I guess my point is dead reckoning and whether we can do dead reckoning in copter. So there's this long thread, RTL without GPS, and so I've been putting a little bit of effort into, trying to set up wind estimation on my vehicle, and I'm wondering, I know maybe you could just talk a little bit about whether it's possible for us to get dead reckoning working in copter as well as it does in plane.
Okay, all right. So so by the dead reckoning, we've and I presented this at the last conference. We have the ability to be able to, by putting in a momentum drag, parameter to capture the momentum drag of the rotors, and then you've got the ballistic coefficients to capture the mass to sort of frontal area. I know that's fairly approximate, and not all copters have bluff bodies, but we put those in, and with a bit of tuning on replay, it's possible to get a reasonable wind estimate, accurate to, well, it's at stronger winds, it gets more accurate as the wind increases in strength. If you're just hovering in light winds, it varies by about 2 meters per second around 0. So light to variable winds doesn't seem to be as sensitive from my experience. I don't know if that's what you've found, Randy. With the,
it seems to be basically, I basically got it working on 2 copters. So it displays the wind speed, and it seems reasonable. Sometimes I'm finding that it doesn't update when I think it should, but I really haven't tested it enough to know. I've done tests in Settle where turning, and this is with just doing some code hacks in the EKF, so it didn't report itself as, it was able to maintain its dead reckoning status just using the drag fusion if it lost GPS, and it was able to fly stably. Like you could leave it in a position hold or loiter mode, but it would drift with the amount of the wind, with the error in the wind estimate and some other. So it wasn't, totally makes sense.
Yeah, it would drift, but it wasn't uncontrolled drift. So in other words, there's a velocity error, but it's a constrained error. It's not that exponential, acceleration and flyway you get if you're flying pure inertial.
Yeah. So are you saying that it should already work, that I should just be able to turn off the GPS and it basically will
I
keep
think
providing an
there's
estimate?
reporting a flag, which I think what it's reporting, I need to check the code. I think it's more of a reporting issue. And then the control loop saying, oh, I don't have a navigation solution.
Right.
So I need to check that.
Okay. Well, but basically, you don't think at this moment, you don't think that we need to do extra software development or nothing major anyway to get the dead reckoning working in multicopters?
No, I don't think so. And it's very much just a backup.
Yeah.
But if it's better, if it extends the time, we can just dead reckon to get you through a GPS, like flying through an area where you get a temporary loss of GPS and lets you get away from that area safely, then that's absolutely worthwhile having.
Awesome. Okay. Well, I'll keep testing. Thanks very much.
Yeah. Oh, now I've just remembered, I was looking at the going through some of the presentations on on YouTube yesterday, and I noticed that Ryan Beale had done his. I think he's introduced some changes which will enable us to use a sort of aviation accepted definition of pressure altitude. And I think there was a question that came up. I wasn't there at the call, but the question came up: what happens if the EKF is trying to correct its origin for the difference between the pressure altitude and the GPS altitude at the same time? And the answer is, by default, we don't do it, but there is a parameter option that enables you to, it's called EK3 OGN mask. I'll put it in the chat window.
Thanks, Paul. I'll talk to Ryan about that.
Yep. All right. I'll just chat that. Put that in the. Put that in the link to that in the window. See if I can find it. Anyway, not quite sure how I get the chat window here. All right. I'll do that afterwards. No, there it is. I found the chat window. Should be fine. That's the parameter. Yeah. Okay. All right. Back to control loops. Yay. So
actually, before since we're on the topic of dead reckoning, I wanted to share one quick story with it. At Krauss and Downey Aerospace, we actually did some testing of dead reckoning for a while on fixed wing, and this is on EKF2, but we were getting fairly consistent, a linear drift of about 1 meter per second.
Yeah, and
we could do that for 20 minutes at a time, and the whole thing would kind of drift linearly, but it was more about a wind error. So I would think more about a wind estimation error, but
yeah, it's surprisingly stable though. So we get I've tested on several aircraft now, and it's always between about 50 and 70 meters a minute, so around a meter per second. And it's a surprisingly constant. You almost wonder if we've got a 1 meter per minute error in there somewhere, right? Because it's just so consistent between different aircraft.
Is it always the same direction?
It'd be worth checking. You mean I'm thinking about this rotation of the Earth or something? Is there some little bias we've got? Because it's just this, quite different sorts of aircraft, quad planes, gliders, big gliders like the Krauss.
I would expect that we could get it down to as little as 0.5 with a very carefully calibrated airspeed sensor. Mm-hmm. It's also
the other surprising thing,
the calibration on the magnetometer
is I tested the same plane with airspeed, compass, airspeed and compass. Then I tested it with just compass, no airspeed. Then I tested it without compass or airspeed. So it was initializing with GPS only, right? And then I did dead reckoning. So when I was dead reckoning, all I had was the IMU and Barrow, and that was it.
Yep.
Right? I had no compass, no airspeed. And the results in terms of dead reckoning performance were very, very similar. right? It was slightly worse without an airspeed and compass.
Were you doing was this doing an orbit?
It was a
As in
circuit.
like
It was a rectangular
okay, all
circuit,
right.
like about 400 meters by about 200 meters rectangular circuit. But the result, even it only has baro and IMU, right? And it still was about 60 to 70 meters a minute. It was remarkably consistent.
That is
Oh,
amazing.
okay, I think this warrants some replay logs and a bit of a dig into that, because yeah.
Because the wind was fairly steady, right? So, you know, if the wind had been variable, the airspeed would have been more useful, perhaps. But yeah, anyway, it's a separate little investigation.
Okay, interesting. Okay, plane height control loops. So the way we currently control height in plane is we have a separate algorithm called TEX, which is Total Energy Control System. And that outputs a demanded pitch angle and a demanded throttle, and it simultaneously regulates airspeed and height. Now, the advantage with doing it that way originally was because it made it very easy to integrate with the existing controllers, because when we added text to ArduPilot back in, I don't know, 2013, it's going back a bit now, we had this interface, which the idea was to use the interface used by the human pilot. So human pilots in FPWAs has control over throttle and demanded pitch angle, and that was the interface that we would use. It was very clean, so we could switch text in and out, nice and easy to integrate. That, as the aircraft, we fitted ArduPilot to go to aircraft that fly faster, particularly or we start to try to do more accurate height keeping, for example, formation flying or precision landings. That methodology starts to run into limitations. And there's a few reasons for that. First of all, if you have an estimation error on your pitch, which could be due to an accelerometer bias, then that error in pitch will cause a bias in the height. And then the integrator in text has to compensate for that. Similarly, for vertical air currents, the integrator in text has to wind up or down to compensate for that. Thirdly, it's difficult to implement put load factor limiting in a way that doesn't result in a degradation of height control. And I think the fourth item starts to become more significant, or at least I see it with my flying, is that if you start to wind the maximum roll angle, roll in CD up to 60 degrees or 70 degrees, because you've got a faster airplane and you want to keep it in that sort of small area and do these tighter turns, the ability to control its pitch angle and its height just degrades when you really start to go for those larger bank angles. And I'll show with this simple little diagram one of the reasons why this is the case. So here we have an aircraft in a coordinated turn. I'm going to ignore side slip, a lateral G. So we have a normal acceleration, which we do need to limit, keep within certain bounds at times. And you'll have a component of that horizontally. That's the component that pulls the aircraft in the turn or pulls it towards the turn. And then you've got the up component, which has to counteract gravity. And there's simple equations that enable you to define that. The problem we have is that pitch angle, because we use Euler angles for our attitude control on plane, pitch angle is really about the elevation of the nose of the aircraft above the horizon. It's essentially an angle above the horizontal. However, if you have a look at our pitch control loop, the correction, we end up with an error on the pitch, and then we apply that to the pitch rate of the vehicle, which is in our body frame, which is a rotation around an axis that runs through the wings. So as you can imagine, is that when we're flying level or small bank angles, that works quite well, because the wings are close to horizontal, and if we need to increase the pitch angle, we demand a positive pitch rate, and that pulls the nose up. But as we start to go more and more, if you like, bigger and bigger bank angles, get to the point in the limiting factor, get towards 90 degrees or 80 degrees, then your control over pitch angle, your ability to control your pitch angle by increasing or decreasing pitch rate becomes less and less. And in fact, as you try to change the height of the change the pitch angle of the aircraft, all you're effectively doing is pulling it into the turn or pushing it away from the turn. So your height control actually starts to affect your horizontal control, if that makes sense. So imagine you've got the aircraft banked over very steeply and you're just using a pitch angle to try and using your elevator to try and control height. Pilots will know that if you've got a steep bank turn and you need to raise the nose, you actually need to reduce your amount of bank angle. You know, release the bank angle so that some of your lift is now pointing up and can raise the nose. So I've implemented a prototype algorithm. I've been flying it on and off for the past 12 months or more, just tweaking it. This has been a slow burn project, and it essentially replaces the concept of a pitch angle demand from text with that. You get an up acceleration from text, you get a turn or horizontal acceleration demand from your navigation loops, which currently we just take from the demanded roll angle because I haven't changed that interface yet. And we combine the two. We adjust the up acceleration to respect our pitch angle limits, and then we also limit our pitch rate, the rotation about the line that runs through it from wingtip to wingtip, that sort of up elevator, it's called bank and yank in terms of turning the aircraft, where you roll the aircraft over until you've got the normal acceleration vector in the direction you need to maneuver, and then you apply pitch rate to change the amount of normal acceleration. So before I carry on, are there any questions there?
Just trying to find the unmute button. Yeah, just related to, we've now got a yaw rate controller, and I wonder whether we're going to incorporate that yaw rate controller. We normally don't activate that in normal fixed wing flight. We've only been activating that in acro mode or in the aerobatics. Does that use of that yaw rate controller the body frame yaw rate controller come into this?
Yes, well, it would, because then you make the assumption that you've got your normal acceleration, and then you have what's called your lateral acceleration, which would be a component of force along the y-axis of the vehicle, out along the wing, out towards the wingtip, and that's what you would control with your yaw controller. Would be that component of acceleration. Now, normally for normal flight, that's zero, but when you go to aerobatics, and you say, I want to achieve a trajectory, but I want my bank angle to be arbitrary, that's where we would actually have a normal acceleration demand and a lateral acceleration demand. And they can be translated to a pitch rate, a rate about the y-axis, and then a yaw rate, a rate about the z-axis. So yes, it could be integrated into this scheme. Okay. Now, in addition to this, I also drilled down and started looking at the TEX total energy control system. That's the algorithm we use to control our speed and our height. And once again, there were decisions made about integrating that algorithm when we first implemented it, which now that we have a wider range of aircraft and a bit more experience with the type, people are starting to use TEX in much more dynamic sort of flight regimes. Some of the limitations are starting to become more evident. Now, TEX does a good enough job for most people. If you're just doing up and away flights, then 5 meters of height variation is really, or 10 meters of height variation in most cases is neither here nor there. So it's all a function of the application. So if I have a look at a block diagram for our current text. I'm going to try and zoom in here. This is zoom in.
Oh, that needs to go on the website.
Sorry, what's that?
That needs to go on the wiki.
Yeah, that's right. That's what we've got. Yeah, I float away. I'm using this stupid Giphy tool to put that together, and I've decided I don't want to use that tool again. It was painful, but I know how to use it now. So anyway, so this is what we do with text. Anyway, what we have with text is we have the, we essentially use what's the concept of energy balance. In other words, the balance between potential energy, which is energy stored in the height of the vehicle, and kinetic energy, which is energy stored in the speed of the vehicle. And the underlying principle that text works on is that your flight path angle, we call it pitch angle, but because we make the assumption that angle of attack is constant, but of course it's not. That flight path angle is a bit like a roller coaster going up the hill, in which case you're trading kinetic energy or energy stored in your speed of the vehicle, and you're trading that for potential energy, which is height energy. And if you want to take energy out of your potential energy bucket and put it into your kinetic energy bucket, then you push the nose down and then you speed up. So it's like one of those classical sort of physics exam questions for the magical frictionless roller coaster in a vacuum, calculating what its speed is and what its height, as a function of its height going along a track. So we essentially do that with, and that's what text is doing. We have what we call an energy balance, which is the balance between our potential energy, which is our demanded height. That's our demanded potential energy. Then we have our demanded kinetic energy, which is our velocity squared divided by 2, because this is the kinetic energy formula, but it's divided by mass. So you won't see mass in these equations because everything's been divided through by mass. So that's what we call specific energy. So we have an energy balance, and then we have the energy balance measured, and the difference between those two, we effectively use that to demand a change in, integrate that error and demand a change in pitch angle. Now, one of the problems we've got here is that integrator appears on the path here for the energy balance. So we got here. So if I'm demanding a height that's well above the height that I'm actually at, so let's assume that my text, you just put a step height input into text, and we try to avoid doing that. We actually rate limit and try to keep the height demands to text within a feasible rate of climb and descent. But for many users, they don't set up their parameters to be feasible parameters. They say, well, they're the default climb and descent parameters, but sometimes their aircraft can't climb at that rate of climb, or it can't sink at that rate of sink. And you end up with the height demand getting ahead of the vehicle. And that integrator, this is just a control systems symbol for integrator. I won't explain. Unfortunately, it's what's called a Laplace transform. I'm sorry, the tool didn't enable me to put in a proper symbol for an integrator block. So anyway, this is our text integrator. It integrates that error, and the integrator winds up until it hits the limit, and it holds at the limit. And then you climb up, you climb up, you climb up, you reach the height, and then it starts overshooting the height. And then the integrator has to wind off, and you end up overshooting your height and then coming back down again until you level off. And this also happens on the other way. If you can't meet your descent profile and you follow the descent down and level off, you can end up with this dip where it sort of undershoots the descent. And that's a bit more alarming, particularly if you're leveling a descent off at 35 meters and the treetops are at 25. So that's one of the limitations there. My instinct with control systems is to usually get the integrator as far down the loop cascade as possible. And so this is the proposed control loop. All right. So now, sorry for those that aren't into control systems and block diagrams. I know it's all very sort of looks very intimidating, or there's a lot going on here. But what's important here is we have our energy balance, the demanded energy balance and our measured energy balance. We multiply it by the gain, or 1 over the time constant. We limit it. That's our demanded rate of change of our energy balance. And we can add some additional compensation here for, for height rate control during flare, where we want a much more closer, tighter control. Then we take the error. So what we've got here now is essentially an error. So we've got the rate of change of our energy balance, the demanded rate of change of our energy balance. That's how rapidly energy is going from potential to kinetic or back the other way. We subtract the measured rate of change of our energy balance. And this is what we call our rate of change of energy balance. That's the error, difference between our demand and our achieved rate of change of energy balance. I know this. So then we just implement a traditional PI control loop with a feed forward term. Now, this has got the advantage that the integrator is now on the rate of change of the energy balance. It's now down 1 loop in the loop cascade, and it means our integrator doesn't hang off and wind up to a large value when we're trying to, if our height demand is not meeting the, if we're unable to catch up with our height demand. So it basically means the integrator is able to respond faster. So a lot of words there. Anyway, they're the block diagrams. Now I've coded this with I've got a prototype branch. I'll just pop the link into that. I've just been fiddling away at this or poking away at it for the past 12 months or 18 months and been regularly rebasing it and occasionally flying it. It's just been a background task. So we've got the branch. You can click on the link and check it out for yourselves. We'd add some additional parameters. Sorry about that, but I don't know which parameters are going to be needed at this stage and which aren't. So I just added a bunch of them because I'm still in the process of developing this. So we can turn this new feature, this new height control methodology on and off in terms of the acceleration vector control. Okay. So now what's important to note is that we are now with these control loops able to run feedback from measured acceleration or measured load factor to demanded pitch rate. You've got to be careful with doing that because if your IMU is behind the CG, the aircraft, it's very easy to end up destabilizing the pitch rate loop by feeding back an acceleration from an IMU that's behind the CG. So you've got to be careful. Once you start running acceleration feedback, IMU location is important.
I presume we're using our IMU position variables. That does fix that, I presume?
No, unfortunately, we can change the velocity, but we don't actually, we'd have to take the derivative of the pitch rate to transform the acceleration to a different point.
Okay.
So we don't have that supported currently. So no, it doesn't, this isn't necessary for this to work. I've loaned it this load factor gain. That's the gain from the normal acceleration error. So you've demanded a certain amount of acceleration on the vehicle, like normal acceleration, and you've got the measured acceleration, and then the difference you multiply by this gain, and that gives you a correction to the pitch rate. You can still fly with this gain set to 0, and there's still a performance improvement to be had, but gust rejection will get better if this gain is able to be turned up. Because what will happen is the plane will hit a gust. There'll be a measured acceleration, and that will immediately pitch the plane down to reduce the angle of attack, and that just reduces it means the acceleration feedback is essentially compensating for the gust rather than waiting for it to feed back through, result in a climb rate, change in height, and then tech's having to put the correction in. We've also got a parameter here which we can compensate for the lag from your pitch rate to the load factor. I've played around with this. It's not very sensitive to it. I don't know if I'm going to keep that parameter, but it's there. There's another parameter where I was looking at the effect of, because a lot of people fly with aircraft which are pretty badly side-slipped. In fact, I'm going to show you an example log after this, where somebody ran into some problems with their roll tuning because of the side slip on their vehicle. So, and this just says if you've got a plane which is generating a lateral G when it turns, you can effectively factor that in when calculating the bank angle required. And then we can limit the load factor. And then there's some other miscellaneous parameters required. For example, I wanted to have text the ability to run a different pitch angle during landing, in landing configuration, because when you lower flaps, the vehicle trims at a different pitch angle. And currently text doesn't take that into account. And also we have within text itself, we have a gain from vertical velocity error to vertical acceleration. So some additional parameters there. I'm still working out which ones would need to be exposed to the user. Okay, so how's it been tested? It's been tested on a little 250 or sub 250 gram flying wing. The reason is this thing's very gust sensitive, very light. I mean, I was flying it yesterday. We had 9 meters per second or more of wind up top sides where I was flying it. And I was pulling a 60-degree bank turns with rapid reversals and in cruise mode and full stick up, full stick down, and getting some really nice performance. So here, for example, is the we can see the this is the demand. Can you see those figures okay?
Yep, no problem. See it clearly.
Okay, all right, good. So you can see this, the red trace, and I set the maximum, the FBW climb rate to 5, plus or minus 5, which is a little bit more than this vehicle can achieve at the top of the, sustained at the top of the climb, but I wanted to be able to really push it and get to the point where it was demanding a height that the vehicle couldn't keep up with, to really, make sure that, show what happens with the integrator. And this is the height profile in green compared to the demanded height profile from the user stick inputs. And this is in 9 meters per second gusty wind conditions. If we have a look at the, that was in cruise mode. And you can see what I was doing with the bank angle, being really vicious to it. So I was literally going full reversal one way or the other. I was doing climbs up and pushing the stick forward and doing these large 60-degree bank reversals at the same time. So really been very unkind to the poor little plane. And then I put it into an RTL, which is a more traditional. That was, I was flying it with the, at about 20 meters per second of airspeed. So really belting this little thing along. So it's very gust sensitive at those high speeds. And you can see the height tracking that it was achieving in the loiter. So the question is, well, okay, that's maybe this is just a very good plane. What does it look like if you fly the old algorithms? So I did that too, where I can turn them on and off with the parameter. And this is more moderate wind conditions. It's hard to get, consistent conditions from, when you're testing it from day to day. So here you can see this is with the legacy pitch, text demanding a pitch angle. And you can see the demand for text, and you could see the green, which is the achieved height. And look what happens here when we're doing these descents. And this is something which I find a bit unnerving. So you demand the descent and then you reverse it. And you can see how it sort of undershoots by about 5 meters, which is a bit unnerving when you're coming in towards a tree line. It's not terrible. That's, for most applications, people find that perfectly acceptable. But then we switch on the new algorithm, and then you can see the difference in terms of the tracking. Now, you don't get it for free. The aircraft is working harder in terms of the rate loops demanding, there's more activity going on. but it does show that the results are consistent with what the theory indicates would happen with implementing an acceleration vector control. Yeah. Okay. So are there questions before I move on to the roll control example?
This is really great stuff. Thanks, Paul. And I'm looking forward to getting this integrated. So we should probably aim for this, to be part of 4.3, the 4.3 stable release. And then we can put out a bit of a call to get more people to test it. I think there's quite a few people that find, the text control difficult to get right, particularly for landing, fixed wing landing. But, even in up and away flight, it can be really quite difficult. So this is really nice move in the right direction. Thanks, Paul.
Yeah, I think this is something I need. That's the next thing I need to do is now start seeing how it works with the flare, and I need to get the little optical flow sensor into that Strix Nano, so I've got a height above ground that I can, a reliable height above ground I can use for the flare maneuver.
Mm-hmm. Hey, Paul, this is Bill Geyer.
Yeah.
So would this be like, is this like a blended G command type, or is this like, so you say vertical normal acceleration control. So are you talking it is like a G command, or is it? Or
it effectively is a G command. So what you've got coming out of text is a vertical G demand, like an up-down G demand. And coming from your path following, the L1 controller is a horizontal G demand, it's actually a bank angle demand that comes out, but the bank angle demand assumes coordinated turns, so you can convert that back to a horizontal G demand. So we have a vertical G demand, horizontal G demand, know what gravity is, do your force vectors, work out what the pitch rate, what the bank angle and pitch rate required is, and then apply the required load factor limiting on the pitch rate. And then it comes down to about prioritization. So if you're clipping on pitch rate because you're hitting your load factor limit, you obviously can't achieve that combination of horizontal and vertical, then the question is, what do you do? And usually you would prioritize height.
Thank you. Yeah, I'd be interested to see how this works in landing configurations and everything. So,
yeah. So I've got to get this into a plane with an airspeed sensor too. That's the other part, is to see how it works with the total energy controller. Because at the moment I've got this little plane that doesn't have an airspeed sensor, so it's just a pitch to throttle mapping.
And Paul, this is Tom Pittenger. Across from Donny Aerospace, we got me and Sam Taber and Ryan Beal that will probably be some good resources to lean on to do some testing on some new text algorithms.
Cool. Excellent. Yeah, it's hard because we got so many different combinations of sensors, people with airspeed sensors, and some people doing flares and others that aren't, and yeah, that'd be good. All right, so how are we going for time? Probably just about out, actually. So
got a few more minutes if you want it.
Yeah, okay. I'm just going to highlight this particular case just quickly, something for people to be aware of. I was sent this log by a former colleague who was setting up I think most of you might be familiar with the Believer. It's nice big fuselage. It's got twin engines, V-tail, and it was set up first flight. I carried parameters across from a previous airframe. Didn't go very well on the first flight. It was pretty sloppy on the tuning. It ended up meeting the bank angle demand. The pilot spanked to the right, and then you can see what's happened is that the pilots then released the stick because the plane's, at that point in time, the plane's getting significantly away because the pilot was using a lot of throttle, so really a lot of airspeed. It was a bit overpowered because because it's been set up for carrying, you know, heavy payloads, cameras and batteries. Release the stick, and you can see here it's taken not 5 seconds for the bank to come off, and that's put it out of position. Then they've gone back the other way. Then the vehicle's departed in roll, and it didn't end well for that aircraft. What was interesting looking at this, and this is something I've seen previously on another twin-engined aircraft, is that I'll load up the file. Is that we make an assumption about zero side slip a lot with our tuning. And this particular aircraft, besides being a little bit underfinned, it's got twin engines. And from my experience, I've come across propellers, and I don't know if it's the case for this aircraft. The propellers are broken and we can't really verify if this was the case. But one of the problems I've run into with twin engine aircraft is that sometimes you can have propellers which are mismatched. They notionally, like it might be, you might get two propellers. They're a 13/7 or 13/8 pitch, and you'd think they're identical. But if you run them on the thrust stand, some of the manufacturers can end up with propellers that are the pitch on the two across two propellers can be different by 5%. So in a 5% thrust variation for the same RPM. And if you've got a twin engine aircraft, that can cause some real problems. So I was just going to show you what this looks like. So for this aircraft, the problem, and I'm just going to show it here. Look at what happens with the lateral G when it's turning. So here it is in a right turn. I'll just zoom in onto this part of the flight. No point taking it past where it's diverged. Okay. So here we are, we're in a right bank at about 45 degrees. It's not track and roll very well at all. There's a pretty sloppy tune on this. And you'll notice that we've got a -1 meter per second squared acceleration on the y-INU. Now think about this, a positive, that means there's a force acting on the body in the negative y direction. In other words, there's a force acting on the body in the direction of the left wingtip, because positive y is the right wingtip. And that means the aircraft, and the pilot did say, well, it looked like it was hanging its nose to the top of the turn. Now, what's happened is that the integrator has wound up in the turn on this aircraft. It's had this side slip on. The integrator's wound up into the turn. Okay, can you see what's happened to the integrator on the roll loop? It's progressively, because it's side slipping, it's got this side slip. Now this is a high wing aircraft, right? It's got what you call side slip stability. It's got a rolling moment due to side slip. So, it's side slipping to the right. It's, essentially it's got its nose to the top of the turn while it's turning right. It's generating this this side force, and that side slip is trying to roll it out of the turn. So the aileron is winding up into the direction of the turn. Then when the pilot releases the stick, that integrator's got to come down again. And then they go back the other way, and eventually it loses roll control. Now I've seen this happen. This is the second log I've seen where this has happened for twin engined aircraft with not much yaw stability. Where they've got themselves into a situation where the eye gain was just not fast enough, just not enough eye gain. If we have a look at the parameters for this log, I think it was, you can see the eye was set to 0.15.
Yeah, that hasn't had an auto tune.
No, it certainly hasn't. Yeah.
Yeah.
This was the first flight. And unfortunately, the pilot didn't have manual. Manual was wasn't available as a mode. The plane got too far away, like lost orientation, switched it to RTL, and then RTL wasn't when it started to depart in roll, and RTL wasn't able to recover it. Of course, it didn't have attitude control, and it ended up destroying the aircraft. So I raise this because for these, something to watch out for is the build up a side slip with a twin engine aircraft, because there's an assumption that I've got two identical electric motors, I've got two propellers of the same manufacturer from the same model, same diameter and pitch, everything's the same. I should have, you know, an aircraft that's not side slipping, and that's not necessarily the case.
Hey, Paul, am I
Anyway,
missing something? So it says IMAX is 0.6, but yet the integrator is going to 16.
Oh, that's 16. Okay, I divide that by 45. So yeah, it's
Yeah, we've got weird scaling.
It's scaled in notional degrees. There you go.
Okay.
0.35.
I was like, whoa.
Yeah,
No thanks.
yeah. Yeah, it was 35%, 1/3 integrator on it. So yeah, second log, I've seen this happen too. The other log, they didn't lose the aircraft, but it was flying really badly, having a lot of trouble coming out of turns, and then wanted to turn back the other way. And it was just the integrator was basically, the integrator was trying to do the job of essentially what we really should be doing with a side slip controller.
We could raise the default integrator so it's a faster speed. Or lower the IMAX, but
yeah,
is this particularly prone because it's a V-tail? With the V-tail, the rolling effect from the tail is in the opposite direction to the yaw effect.
Well, if I graph AETR dot, I look and
you actually get the tail competing with the ailerons in a V-tail.
yeah, there was mixing going on with, they did have rudder mixing, you can see.
Yeah.
So yes, it was an unhappy airplane. I don't know how much is due to the fact that propellers were mismatched on it. How much was the fact due to that? I don't know where the CG was for this test, and how they're not known for their directional stability. These airframes, they're not optimized for that.
One thing is we don't turn on the yaw damper by default.
No, I don't think the yaw damper would have helped unless they turned on. They would have had to have had the yaw damper on and tuned, or at least on, and they would have had to have had the side slip controller gain turned on.
Yeah. We could think about whether we're going to, enable those by default. If we could make those automatically tune themselves, then actually have the side slip controller enabled.
Yeah, I mean, you can see here, I had differential. I mean, and also they weren't running differential thrust for rudder either. So it was just I had two servo outputs with function 7.0, which I think is just normal throttle. So they weren't running differential on the throttle. Yeah. So anyway, it's a bit hard to do an inspection of the airframe now, and I think there's not much to be gained other than what we can glean from the log. But anyway, it was interesting to see how the side slip that came in and really fought the aileron, and how that integrator wound up. Like that.
I mean, if you run an auto tune, the Believer really does fly very nicely.
Oh yes, they do.
But you need to have done that auto tune on it. And, we haven't got the sort of frame parameters. A Believer is probably common enough. We should just have the tuning parameters up as a thing to download. Because
indeed, we actually have a wiki page, I think, which is sort of hanging there, waiting for some love.
Yeah, because the Believer is definitely a common enough frame that the fixed wing tuning parameters. I mean, of course, it depends on, unfortunately, the throws you've got. And so people set up different throws on the same, because they use different servos and.
Yeah, the cleaver's in a different thing on the control horn. You just don't have, we don't have control over that.
Yeah, and I've also heard that very good success with reverse thrust on that as well.
Yeah, that can work well. You were testing that, Tom, I believe.
I wasn't. No, there's someone
Okay.
else. I've never actually used
I
any
know it's a
dual
popular
engine
airframe
aircraft
with-
like that.
I know it's a popular airframe with people doing mapping.
Yeah,
because they can
it's
carry
also a
bunch of
VTOL
stuff.
variant. The Freeman 2100 and 2300 are just the same airframe, but with VTOL available. It's quite a popular airframe. I've got one myself.
Yeah, I'm just checking out the speed. It was moving 25. I don't think the airspeed sensor wasn't calibrated. So, but yeah, it's going pretty quick. That's why the turns were taking up so much space.
Now, this might be a little off topic, but something internal that we've been talking about is you're talking so much about Sideslip there. My mind was wandering a bit. We were looking at adding intentional Sideslip for air brake.
Okay.
Yeah.
Yes.
Thoughts?
Now that can work that can be very effective. So, I mean, I've done that in cruise mode just with a rudder mix in where the planes I've been flying along and literally yawed the plane, and you can actually see the nose will yaw off, the roll loop will keep the wings level, and you can actually see how the throttle has to ramp up to maintain the airspeed.
Yeah, we've certainly done it on accident a bunch, and it happens inadvertently all kinds of times. But it'd be nice to actually have a negative throttle that could sort of feed into that, somehow.
We could have it as like a virtual flaps, because basically you could just add it onto the rudder and then just let the roll loop and the navigation controller compensate. So you could actually just have that as an option of, proportional flaps onto rudder.
Yeah. The reason I'm thinking that this aircraft either wasn't trimmed straight or it's a differential thrust issue on it was even when it banks back the other way, you could see that it still wants to yaw in that one direction. Still got that side slip to the right. That's interesting.
Yeah, we have seen that. There's another log I was looking at just a few days ago, which has significant sidestep, and we're still trying to find the cause of it. It was one of the partners flying a quad plane, and it's just constantly sideslipping, and I haven't yet managed to find the cause of that. So I might ping you later and see if you can work out what the cause is.
Yeah. Anyway, it was a curious log, but it's the second time I've seen this effect, so I thought I'd bring it up.
All right. Thanks, Paul.
Nice.
So, are there any final questions for Paul before we move on? All right. That's in, Paul. Then I'll get you to stop screen sharing, and we'll introduce the next speaker.